Hey folks, we are on the last worksheet for solutions, specifically solution stoichiometry. So before we get too far into our worksheet, let's remember what stoichiometry is. Okay, stoichiometry is the relationship between moles of one thing and moles of another. So you'll notice this has a 2 in front of it and this has a 1 in front of it. So this tells us that 2 moles of hydrochloric acid react with 1 mole of magnesium hydroxide. So it's very important you realize these are all molar relationships. We're producing 2 moles of water, 1 mole of magnesium chloride. Okay, so as a result, those are our relationship of moles to moles, and we need to know what those are. Now, the bottom line when we do this is every problem that we do has to be a mole-to-mole problem. Well, to get to moles, sometimes we don't have moles. Sometimes we have grams we have to convert. Sometimes we have a molarity of a solution. And remember, molarity is equal to moles per liter. So if we're given a molarity in a certain number of milliliters or liters of something, we can then calculate the moles by saying the moles are equal to the molarity times the liters. Now hopefully you don't have to write that down. Hopefully you can just figure that out from what the molarity equation is. Right. So given that information, sometimes we'll have to do that first and then do some stoichiometry, or sometimes we'll have to do the stoichiometry first and then do the conversions next. Okay, so let's look at some problems. Right. How many grams of silver chloride are produced when 40 milliliters of silver nitrate is reacted with sodium chloride? So let's create a balanced chemical equation. We have silver nitrate, and we're reacting with sodium chloride, and notice it says excess NaCl, so I have more than I need, so I don't have to worry about that being a limiting reactant. Right? This is a double replacement reaction, so it is going to produce silver chloride, and it's going to produce sodium nitrate. Sorry, that's a plus sign. Sodium nitrate. Everything has either a +1 or a -1 charge, so everything cancels out. We have a balanced chemical equation, so we have a 1-to-1 to 1-to-1 relationship. That's nice. So it's asking us for how many grams of silver chloride are produced. Now because it's asking for grams of silver chloride, we have to figure out how much this weighs. So if I look at silver, silver weighs 107.87 grams per mole, and chlorine weighs 35.453 grams per mole. So when I add these things up, I get 143.32 grams per mole of AgCl. So what I'm given here in the problem is I'm given 40 milliliters of a certain molarity of something. So I do have to find moles. So molarity is equal to moles per liter. So therefore moles is equal to molarity times liters. My molarity is 0.25, and my liters, well, I'm given milliliters, so I should be able to do those conversions in my head. So 0.040 liters. Right, so when I do that math, that gives me a total of 0.01 moles. All right, well, what is that? That's moles of silver nitrate. Now, what do I want? Well, I want grams of silver chloride. So I can go from moles to moles. That's my stoichiometry piece. So I start with 0.01 moles of AgNO3. But I don't want moles of AgNO3. I want moles of AgCl. Alright, but am I done? No, because it's asking me up the top. The question is all about grams. Alright, so I have to go from moles of AgCl to grams of AgCl. Now, if I look at my equation, I'll notice all my coefficients are 1, so 1 mole of silver nitrate gives me 1 mole of silver chloride. And 1 mole of silver chloride, I had to figure out how much it weighs. That's way up here. Alright, so that is 143. Sorry, I lost my cursor again. 143.32 grams in 1 mole. So now I multiply all that out, and I get 1.4 grams. Notice I only have 2 sig figs because I've got 2 sig figs in my problem right there. So my answer is going to have 2 sig figs. Okay, and this is grams of AgCl. Okay, that's that problem. Let's try another one. We have excess hydrochloric acid, so hydrochloric is not my limiting reactant. So I have 45 milliliters of this sodium bicarbonate solution, which is 45 milliliters and 0.100 molar. Okay, and it's asking me how many liters of carbon dioxide at STP. Liters at STP. Well, the nice thing is I don't have to use PivNert. So, okay, we're given this information. We have to figure out, we have a molar relationship. All of our coefficients are 1. So we have to go and figure out moles. So let's see. Molarity is equal to moles per liter. So my moles are equal to my molarity times my liters. My molarity is 0.1, and my liters are 0.045 because I'm told it's milliliters, right? And there are 1,000 of those in a liter. And so this comes out to 0.0045 moles. All right. Well, I'm certainly not done. I have to take my 0.0045 moles of sodium bicarbonate, and I have to convert from moles of sodium bicarbonate to moles of, well, what's my target? How many liters of carbon dioxide? So I'm going to carbon dioxide, because that's what it tells me here. I'm going to carbon dioxide. But I don't want moles, I want liters. So I have to convert from moles of CO2 to liters of CO2. Well, if you remember, at standard temperature and pressure, there are 22.4 liters of any gas in 1 mole. And when I look at my equation up here, all of my coefficients are 1s. So I simply take the 0.045 and I multiply by 22.4, and that gives me 0.1008, which we have 3 sig figs in our problem. I think that was 45.0, if I remember correctly from what you were doing. So it should be 0.101 liters of CO2. Okay, that's number 2. Okay, excess zinc. Aha, another one of these things where we have an excess. That's real nice. Zinc reacts with hydrochloric acid, that's HCl, and it produces a single replacement reaction. So this is going to be H2 plus zinc chloride. Now zinc has a +2 charge and chlorine has a -1, so it's zinc Cl2. That means I have to have a 2 in front of here, and so now I'm balanced. So the question is, how many liters of hydrogen gas are produced at 585 torr and 50 degrees Celsius? I think I spoke too soon. It looks like this one's going to be a PivNert problem because I'm not at standard temperature and pressure. All right, so let's figure out first how many moles of hydrochloric acid I have. Okay, so that's up here. So I have to figure out how many moles of HCl I have. So we start with, let's see, molarity is equal to moles per liter. So moles is equal to molarity times liters. So moles is going to be the molarity is going to be 0.50, and the liters are going to be 1. So it's 0.50 moles is that answer. So that's how much HCl I have. Now, if I take 0.50 moles of HCl, what I'm trying to figure out is, I'm going from here, I'm trying to figure out H2. So I have to get rid of moles of HCl and go to moles of H2. Well, I have 2 moles of HCl making 1 mole of H2. And I guess I'm done because I can't figure out liters directly here. I can't just multiply by 22.4 because I'm not at STP. So I'm done here. So I take 0.5 divided by 2, and that gives me 0.25 moles of H2. All right. So again, I'm not done. I have to do PivNert. Right? So let's think about PivNert for a second. PV equals nRT. Right? The 0.25 moles is to N. And our volume is given to us, oh gee, we've got, let's see, how many liters? That's our unknown. And our temperature is going to be 50 Celsius, and 50 Celsius plus 273 gives me 323 Kelvin, so that's 323 Kelvin. And it's asking me for liters in my volume, so I'm going to use the 0.0821, which is liters, atmospheres, moles, Kelvin. So I have to convert my pressure into atmospheres. So let's do that. 500 and, well, let's stay over here. 585 torr, and that's 760 torr in 1 atmosphere. So if I take the 585 and I divide by 760, what do I get? I get 0.769. I get 0.76974 ATM. Guys, again, I keep more sig figs than I need, and then I round at the end. Okay, so if that's how many atmospheres, that gives me my pressure. So I've got everything I need. I know my R, 0.0821. So I think I'm done. I think all I have to do is solve for volume. So volume is going to be equal to nRT over P. So the number of moles is 0.25. And my R constant is 0.0821 liters, atmospheres, moles, Kelvin. And my temperature is 323 Kelvin. And I'm dividing by my pressure. And my pressure is, what's my pressure? Pressure is 0.76974 ATMs. All right, before I go any further, I'm going to check my units, and I notice ATMs cancel. I notice that moles cancel, and I notice that my temperature, which is in Kelvin, cancels. And so I am left with liters, which is what I would expect my volume to be in, because that's what I asked for. And my answer here is 8.6 liters of gas, specifically hydrogen gas. And that's a lot of hydrogen gas. Okay? All right, let's try number 4. All right, lead chromates produced from the reaction of sodium chromate. Okay, let's go and write some things down. This is sodium chromates, NaCrO4, and lead 2 nitrate plus lead 2 nitrate. All right, and so obviously I have a double replacement reaction, so I'm going to put together lead and chromate, CrO4, and I'm going to put together sodium and nitrate, NaNO3. Okay, let's see, what do we have with charges? Well, we have a +1 for sodium and a -2 for chromate, so I have to have 2 sodiums. And lead is a +2 and nitrate's a -1, so I have to have 2 nitrates. And lead's a +2 and chromate's a -2, so that's cool. And sodium's a +1 and nitrate's a -1, so that's cool. So we're done balancing our charges. Now let's go back and balance the number of units that we have. Well, we have 2 sodiums on the left and we only have 1 on the right, so we have to put a coefficient of 2 in front of the sodium nitrate. We have the same number of chromates, same number of leads, and we have 2 nitrates on the left, and we now have 2 nitrates on the right, so we are now balanced. All right, so what do we have? We have 4.50 grams of lead chromate, and it is produced. Hello, where are you? Thank you. 4.50 grams are produced from the reaction of 100 milliliters of sodium chromate, right? 100 milliliters of sodium chromate and 100 milliliters of lead nitrate. What's the initial molarity of the lead nitrate? So we have to assume that the lead nitrate is not in excess. So we're going to make that assumption, and we're going to work backwards to our lead nitrate. Okay. To figure out our initial molarity of the lead nitrate. Now I have to be careful. We're talking about the initial molarity of the lead nitrate, not when it was combined after with the sodium chromate, because we had 100 milliliters there. We're only dealing with the 100 milliliters of the lead nitrate. Okay, so what do we have to do? Well, we have to work our problem backwards, because we're given 4.5 grams of lead chromate. So we have to figure out how much lead chromate weighs. Right? So we're going to take the molar mass of that, and that's lead is 207, and chromate's 52, and for oxygens is 64. All right, so we add all those up, we get 323.2 grams. All right, that's our molar mass per mole. All right, so if I start with 4.50 grams of lead chromate, PbCrO4, and I get rid of grams of PbCrO4, and I go to moles. Oh yeah, moles of PbCr. 04. Yeah, got to go to moles. Okay. Now that we're at moles of lead chromate, we can switch from moles of lead chromate, PbCr04, to moles of our starting substance. Now, in our case, moles of our substance that we're looking for is lead nitrate. Okay. So we have to go back to lead nitrate, PbNO3, and that will give us moles of lead nitrate. Okay, why do we care about moles of lead nitrate? Let's kind of just step aside for a moment, because molarity is moles divided by liters. So we're trying to figure out the top half of this equation. All right, let's go back. We know that how many grams are in 1 mole? Well, we said 323.2 in 1 mole, and I look at my coefficients. And I have lead nitrate over here, and I have lead chromate over here, and I have a 1 in front of both of them. So my 1 and my 1 are going to cancel. All right. So I take the 4.5, I divide by 323.2, and I come up with what do I come up with? Well, that's moles of lead nitrate, right? So when I come up with moles of lead nitrate, that is going to be 0.013923 moles. Again, I'm keeping too many sig figs because I don't want to lose significance until the end when I'm going to round. So that's 0.013923 moles, and I have to divide by liters, right? And my liters are, as molarity is per liter, I have 100 milliliters, so that's 0.1, or 100 milliliters. All right. So now when I do that, how many times will 0.1 go into that? It will go in 0.139 molar. Right. And again, I believe I'm supposed to have some zeros up here, 0.0 and 0.0, so I believe I have 3 sig figs. So my answer is 0.139 molar is the solution, is my initial solution of PbNO3. 2. All right. This one's going to take a little bit longer. Number 5 is actually a limiting reactant problem. Okay, so if I look at this, let's go and figure out my problem. It reacts with this, so I have potassium iodide. So I'm going to stick this way up here because I'm going to need the room. Ki, potassium iodide reacts with lead nitrate, PbNO3, and we know that that's going to be lead 2 nitrate, so that's a 2 down there. We've already figured that out. And now this is going to produce as a double replacement reaction, so it's KNO3 plus PbI2. Alright, so now when I balance this, I'm going to have 2 of these, and I have to have 2 of those to make it balance. 2 I's, 2 K's, 1 Pb, and 2 NO3s. Great. Okay. How many grams of precipitate? Ooh, which one of these 2 is precipitate? Well, I can look at this, and if you remember your solubility table, you'll know that anything with potassium and anything with nitrate, these are both aqueous. So this must be my solid, and in fact, if you look it up on the periodic table, on the solubility chart, you will find out that lead iodide is the solid. We're trying to figure out how many grams of it are formed. So we have to figure out how much lead iodide weighs. I'm not going to waste your time, but that's 461.0 grams per mole. And we're going to have to go and work through figuring out our molarities, our moles. So remember that molarity is equal to moles per liter. So moles are equal to molarity times liters, which is going to be equal to, in this case, 0.75 molar, and we're multiplying by 0.050. So our molarity in both cases is going to be 0.0375. Now, I don't need to go through both of these because I've got exactly the same numbers for both. Okay. However, when I go to my stoichiometry problem, now that's different. Okay. So we're trying to figure out how many grams of lead iodide we can form. So let's do that. We start out with 0.0375 moles of Ki. We're also starting out with 0.0375 moles of lead nitrate. Okay, so now what we have to do is figure out how many moles, no, how many grams of lead iodide we have. Well, let's go through this first one. I'm converting from moles of Ki to moles of my target substance, which is PbI2, and then from moles of PbI2 to grams of our target, which is PbI2. And we figured out that the grams of PbI2 is 461.0 in 1 mole. And if I look at my coefficients, I've got a 2 in front of the Ki, and I've got 1 in front of lead iodide. Okay, that's good. So now we have to do the other one. And now we can actually just plug and chug and see what happens. Well, here we're going from 2 moles of Ki, just like we were before, to, I'm sorry, try that again. We're going from 1 mole of lead nitrate, PbNO3, 2, because that's the units that are up there, that's units that come down. We're going from 1 mole of that to 1 mole of PbI2. All right, before we go any further, look at your coefficients. You'll notice you've got a coefficient up here of 1 and a coefficient over there of 1, so it's a 1 to 1, so we're okay. All right, so now what do we do? Well, now we have to go from moles of PbI2. This is the part that's exactly the same as the one above it, PbI2, and we're going to grams of PbI2. Okay, and that's 461.0 in 1 mole. All right, so we do this math, and what we come up with is this is 8.6 grams. We do the math down here, and we come up with 17.3 grams. So obviously, this is the one that created less. Hence, this is the one that's your limiting reactant, which is moles of Ki. So moles of Ki is your limiting reactant, and how many grams of precipitate are formed? The maximum you can create, or 8.6 grams. All right, folks, that's solution stoichiometry. Again, if you feel you need more help, let us know. We'll be happy to provide you with some extra problems and go over this with you anyway. Okay? Have a great day. We'll see you later. Take care. Bye. Whoa. Sorry, I missed a question. Explain why the boiling point is elevated and the freezing point is lowered in the solution. No, we did that last time. Sorry. Ignore that. We'll see you. Bye.